All right, so we're going to tune this integrating process that we've seen earlier in our lab and some of our other labs in this course. Just a quick recap. We have a level we're controlling in this vessel. We're measuring it with this differential pressure transmitter down here, measuring the level. This valve right here is controlling the flow from our pump, which is right down here. The fluid's coming up through our flow meter into our valve and then in to the top of our process over there. And then what makes it integrating is from the bottom here, we're sucking our, let's just maybe take you around here. This angle probably help. So up the bottom of our vessel, comes down, flows down here, and then it flows down and over to our suction of our other pump over here. And then out of the pump, it comes up here and around, and then up and over and through this flow meter here, and then through this globe valve before then it's discharged back over here into our tank. And then it just kind of circulates around because our pump over here is drawing from the tank, and it's just a continuous loop like that. So this pump over here off the bottom, that's what makes it an integrating process for us. So I'll take you guys back over here. Everything's flatlined. What we're gonna do is we're gonna tune this with Ziegler-Nichols closed loop. So if I click here, it brings up, we can get our tuning parameters right here. I set the reset to a really high value. It essentially turns it off. It's easy for us. It's the easiest way to do it without having to go in and changing any programming. Set this for a really high value. I set the gain to 1. And now what I'm going to do is I'm going to put the controller here into automatic, because in Ziegler-Nichols we need to have our Ziegler-Nichols closed loop. The loop's closed, so we need to have it in auto. So now that it's in auto, we had it at steady state before. Now what we're going to do is we're going to go ahead and give this a set point change. So I'm going to bump it up to 56. We'll do a 10% bump. So we're going to bump the process and then see if it goes into oscillation. So you can see there, it's not oscillating. So we're gonna go and increase our gain again. So I'm gonna increase it. I'm gonna go up by 2 each time, by a factor of 2. We'll drop this back down to 46 and see what our process does. So it's responding faster here. This is kind of what we expect to happen with an integrating process. If it's pure integrating, it shouldn't oscillate, but we'll see. There's probably some dead time in here due to the control system, and we should be able to get it to oscillate. We'll see. Still no oscillation, so we're going to bump this up to 4. Oops, not 40. 4. Do another step change and go back up to 50%. Oops, we went too high there. Oh no, sorry, we never. Just saw this spike, but that was fine. Okay, still nothing. Let's go and increase this again. We'll go to 8. And I'll bump this back down to 46. Notice how each time we've changed the gain, the response time of our closed loop here has increased. So here we're starting to see our first little bit of oscillations show up. This was a pure integrating process, that would not happen, so there has to be some dead time in the loop that's causing this. Let's maybe go to, yeah, we'll go to 16. Keep doubling it. So it appears we do have a slight oscillation, but it's still diminishing. You can see we were really quick up to our 56. So over here we're getting pretty close to 56. We have very minimal offset because our gain's so high, it reduced our offset. So let's try increasing this maybe a little bit more. We'll just go to 18. We're pretty close to oscillations. Bump this back down to 46. Try increasing our gain a little more. Give it another bump to get the process moving again for us. So because it's an integrating process, we may have trouble getting this to oscillate completely. So let's just go really high for the sake of it, just to see. We were at 20. There you can see that's showing us that we do have dead time here because these oscillations are now growing. So we'll slow this back down. Try 30. See if our oscillations stabilize. Try 35. So it's looking like right around 35, the oscillations are remaining, they're fairly stable. So now with Ziegler-Nichols, we'd want to apply our tuning factors. So whether it be for a proportional only controller, it would be easy. There's one calculation, we only need the one variable. which is our controller gain over here. We're at 35. Looks like we are slightly growing here. I might just back this off. We'll try 32. So 32, maybe a little bit better of a value. Right around that 32 mark. We'll use 32. If we look at our period of oscillation here, it's right around 8 seconds. It's about 2 divisions from peak to peak. So we're about 8 seconds for our period of oscillation. So we can use that value of 8 seconds and use our gain value of 32. So since it's an integrating process, it has a very high gain value. So what I'm going to do now is I'm going to calculate the Ziegler-Nichols values for both proportional and proportional plus integral controller and compare the closed loop response. So I'll go ahead and do that now. All right, so I've entered in the tuning parameters for just a proportional only controller. You can see that it's doing quite well for our offset wise. We're about 40. Right around 40 is what we're holding at here. This blue line, it's doing quite well there. You can see there's a little bit of oscillation in our control valve still, so if that is a concern, you'd always want to lower your gain, and that should help reduce a little bit of that. So really technically, because this is an integrating process and we had such a high value to get it to oscillate, that really reduced our offset, and we technically wouldn't even really need proportional plus integral here. But what I'm going to do is I'm going to go ahead and key in, calculate those values, proportional plus integral, and update this and just see how it if it affects our response at all. And I guess I should also show you a set point change here. We're going to go from we're sitting at 40 right now. We'll go up to 50%, and we'll just see how everything works here. You can see our valve spiked up right away. It has that high gain, and you can see that our levels ramping up now, and we should see something that looks close to quarter amplitude decay here. It'll really show up in our valve signal, and so there you can kind of see it. The oscillations they're decaying. Our gain might be a little bit higher maybe than it needs to be, but they are decaying. So it got up to the set point quite quickly, and we have very small offset. So I'll go ahead and key in those values for proportional plus integral. All right, so I've keyed in our proportional plus integral settings. You can see here we're just sitting here steady state. Valves maybe oscillating a little bit, but not too bad. And if we look over here, we're right at our set point, right? We're right at 50. And I'm gonna go ahead and make a set point change here, and we'll go up to 60. And we'll just see how everything responds here. So you see it ramping up, and there we should see something that looks like quarter amplitude decay again, because we used our Ziegler-Nichols closed loop. So there's our valve kind of oscillating back and forth in black. And then what we should see eventually is it stabilize with no offset again. So the valve is, you can see it's dampening off, the oscillations are dampening off. And if we look over here, we're right at our set point of 60. So that's what that integral is going to do for us. It's going to remove that offset, and it's doing quite a good job here. So there, we've tuned our integrating process, integrating liquid level process with Ziegler-Nichols closed loop. All right, so I've configured the process trainer here, reconfigured it for a flow loop. You can see down here at the bottom, pumps up discharges up through our flow meter here. And now we're going to be controlling flow. So we're going to tune a flow control loop here, and flow is quite a quick process. So you'll see that on our trend. Flows through the flow meter, in, loops around, up through the valve, and then comes out through the valve and is discharged. You can see it is unioned up right here and then flows down into our tank right there. So it's just a continuous loop. We're just basically pumping fluid through this flow meter and controlling flow with this valve in the loop. So take you over to the screen here. I guess we should turn on our pump and we'll have a look over here. So you can see the valve. I had the valve at 50% open. That's what this black line is right here. It's at 50%. And right away the flow came up and stabilized, self-regulated. So it didn't take long. It's pretty much, it's even like almost just like strictly, not much of a first order there at all, but there is a slight one, and it's probably actually more due to the electronics in our flow meter up here. So but we got to tune for that because that's part of the loop. So what we're going to do is we're going to perform a Ziegler-Nichols closed loop tune here. And so if I bring up our tuning parameters, you can see I've already got the reset turned off with a really high number. I've got the gain set for 1. So what I'm going to do is I'm going to put this loop, right now it's in manual. Manual just set at 50%. I'm going to put it into automatic here. Right there, I just clicked auto. And what we're going to do is we're going to bump our set point. So notice our range here is 0 to 15 liters per minute. And that would be basically the same thing as 0 to 100%. 15 would be the 100% there. So we'll bump this up, I don't know, 2 liters. So we'll go to 8.8 liters. And we'll just watch to see what our process does here. See if it oscillates at all. It does look like there's some oscillation there. We'll just wait it out for a little bit just to see if it dies off or not. It does look like it's shrinking some. What I might actually do, I think because we're interfering with everything right here, what we'll actually do is we're going to tune this at a lower value. So let's put this in manual and let's drop our flow down to 25 just to see, or our valve to 25, just because they're overlapping there. This might well, we're down pretty low. Let's tune a little bit on our higher end, I think might be a better bet. So let's tune up around 65%. We'll open our valve 65% and see where that puts us. A little bit above. So there might not be as much interference now. So let's try this just to see, because we were kind of interfering there. We'll just see how this looks. Put this back into auto. And we'll step this down to 8. And let's just see. It looks like they might still overlap a bit. Might not be able to get away from this. So what we're watching here is the blue, the process variable, and it's slowly diminishing. So that means we need a little bit higher gain here. So I'm going to go and bump the gain up. We're going to set that to, I don't know, 1 point. Doesn't look like we need too much, so we'll try 1.2. See what that does to our oscillations here. It actually looks like they might be growing. But not too bad. Maybe just knock that back down to 1.1. Just watch to see what happens. Just wait it out for a little bit. We're probably pretty close. Since it is so fast, the wave almost looks square and choppy because of our update times here, but I think we're gonna say 1.1. It's probably pretty good. kind of growing a little bit, or decaying a little bit, sorry. I'll try 1.15. Alright, so my plan here, what we're going to do is we're going to tune this process. Ziegler-Nichols, we've got it oscillating right now, so we need two values. We need our gain value here of 1.15. We also need to determine what our period of oscillation is. And so each one of these divisions is about 4 seconds. So if we look from peak to peak, we're about 3 seconds between each peak. So we've got a period of oscillation about 3 seconds, and our gain, our ultimate gain of 1.15. So we'll go ahead and make the calculations here, and I'm going to update them and put them into the tuning parameters, and we're going to see what that does for our response to a set point change. Alright, so I've just finished putting in the tuning values here. You can see it's stabilizing around 8 liters per minute, and you can see there's no offset because we're using integral. So what I'm going to do now is I'm going to make a set point change. So let's knock this down to 5 liters per minute, and let's just see how we use Ziegler-Nichols, so there should be somewhat of a quarter amp decay. You can kind of see it came down and now it's kind of stabilizing again at a new value, and we can go up as well. So let's bump this up to 10. So change our set point up to 10, and right away you can see our controller output jumped up, and the process responds quite quickly because we're dealing with flow. It's a fast process. And there you can see it looks like the process went up, overshot, came down, overshot, and it's stabilized. That looks pretty well like quarter amplitude decay. So it looks like our Ziegler-Nichols closed loop tune worked quite well.